All right, so now we're going to talk about how to solve tridiagonal systems. All right, so let me give you the definition of a tridiagonal system. So a linear system of equations, ax equals to b, right, is said to be tridiagonal right, if aij is equal to 0 whenever the absolute value of I minus j is greater than 1. Okay, so that means that I can write this matrix A in the following way. There's a diagonal u1 to un. There's sort of just one up, w1 to wn minus 1, and then just one down, there's a v2 to vn. Okay, so let me state the following theorem about tridiagonal systems as it relates to LU decomposition. So a tridiagonal matrix A, right, can be factored into a lower L and upper triangular matrix as follows. Okay, so I can write A is equal to LU if A is tridiagonal, and it has a very particular form. So it has alpha 1 all the way up to alpha n, v2 up to vn, so the same v as before, times an upper triangular matrix which involves 1s along the diagonals and gamma 1 to gamma n minus 1 just above that, where alpha 1 is equal to u1, gamma 1 is equal to w1 divided by alpha 1, then alpha I is equal to ui minus vi gamma I minus 1, and gamma I is equal to wi divided by alpha I. This is for I equals to 2 to n. This is for I equals to 2 to n minus 1. Okay. All right. So, so the theorem is kind of nice. It tells you exactly what the LU decomposition of a tridiagonal system is, and you can see that it requires order n operations to write down what that LU decomposition is. And then you can also check that the forward and backward substitutions are cheap as well, because each operation now, because of the fact that it is banded, it requires only a finite number. Well, it only requires sort of a sort of order 1 number of calculations to do the forward and to do each of the terms in the forward and backward solve. So it's order n. It's like to do the whole forward and backward solves. Okay. All right. So so actually, let me just write that down. Right. So you can solve. LU x equals to b using forward and backward substitution, right? Okay, and so let's look at the forward part. So this is Ly is equal to b, right? y1 is equal to b1 divided by alpha 1, and then yi is equal to bi minus vi yi minus 1 divided by alpha I. And this is for I equals to 2 to n, right? And then the backward substitution is ux is equal to y. And here xn is equal to yn, right? So it's backwards. And then xi equals to yi minus gamma I xi plus 1. And this is for I equals to n minus 1 all the way n minus 1 down to 1. Okay? All right. So we can put that all together. It's like and do the tridiagonal solver. So let's go ahead and do that. All right. So I'm just going to erase everything, and then we'll go ahead and do the tridiagonal solver. It's really sort of just taking those expressions which I've written down, it's like, and then writing it or transcribing it into code. Okay. So the algorithm for a tridiagonal solver. All right. So your input are these three vectors, u, v, and w, which correspond to the the diagonals. It's like and the one just above and just below, right? The right-hand side is the b vector, and n is the size of the matrix, and the output is x, which is the solution to ax is equal to b. Right, so the first part is the LU decomposition. Okay, so alpha 1 is equal to u1, which we wrote down. Gamma 1 is equal to w1 divided by alpha 1. Again, wrote that down. And then we just do a for loop for I equals to 2 to n. You do the following. Alpha I is equal to ui minus vi gamma I minus 1. And that. And then for I equals to 2 to n minus 1, I write down the gammas. Gamma I is equal to wi divided by alpha I. You end that. So that gives me the LU decomposition, right, in the form which was stated in the theorem. Okay, so now I can do the forward and backward solves, forward and backward substitution. So this is the forward substitution. Okay, yi is equal to b1 divided by alpha 1. And then for I equals to 2 to n, you do the following, that yi is equal to bi minus vi yi minus 1, whole thing divided by alpha I, and you end the for loop. Okay, and then there's one more step, which is the backward substitution. Okay, and so xn is equal to yn, right, which is sort of what we have from, again, the expression I just wrote down. And then for j equals to 1 to n minus 1, and then I actually want an index which goes to n minus 1 to 1, so I is equal to n minus minus j. And then xi is equal to yi minus gamma I xi plus 1, and then you end the for loop. Okay, so yeah, so this simple code implements the LU decomposition for a tridiagonal solver, and then does the forward and backward substitutions in order to give you the solution of the tridiagonal system. Okay, so this is big O of n flops, right, in contrast to the usual big O of n cubed operations for LU. Sort of for LU for a full matrix. Okay, so the fact that it is tridiagonal makes a huge difference in terms of the computational efficiency of this solver. All right, and so let me finally then say something about the error associated with clamped cubic spline, and then say how you can call this in MATLAB. Okay. All right. So the error for clamped cubic spline is, if you look at the max error between A and B of f of x minus s of x, this is less than equal to 5 over 384 h to the 4 m, where we need that f is at least 4 times differentiable on the interval, and m is the maximum of the fourth derivative on that interval. Okay, and h is the maximum length of a subinterval. Okay, and if you want to call a MATLAB routine, it's like for doing spline interpolation, then you can do this. There's what is called the inter P1, it's a 1 I think, so command and the input is x, which is a vector of nodes. F is a vector giving you the function values at the nodes. And z is the vector of points where you want to evaluate s. Which is your spline interpolant. And then the output is fc, which is a vector of s evaluated at those z points. And so the way you call it is fz is equal to inter p1 x f z, and if you want to do linear interpolation, you just call linear. Right, so this is linear, piecewise linear splines. And then if you want to do cubic, it's the same routine, except that instead of linear, you just call spline. And then this is cubic splines. Okay. All right, so that's just a sort of quick introduction. It's like to splines, and again, one of the most commonly used, I mean, there's sort of two very commonly used splines, the piecewise linears, which you've probably seen before, and then the cubic splines are also a very commonly used spline as well. Okay, so yeah, so that's all I really wanted to say about spline interpolation. There's of course a lot more, it's like which one could talk about, but again, for the purposes of this class, this is just sort of a brief introduction to the most commonly used splines which we have out there. So let me just stop here for now.